Hello everyone, I am Sahana Kulkarni. Today we will going to discuss regarding the next chapter, that is moving charges and magnetism in this first session. First of all, we will discuss regarding the introduction of this chapter. So in earlier days, or we can say in olden days, it was thought that both electricity as well as magnetism, they don't have any relation between them. Therefore they will study this in different subject, or they are thought it as they are the separate subjects. But in case of in 1820, Danish physicist, that is Hans Christian Ørsted, he demonstrated that electricity and magnetism both are interrelated with each other and both are having certain relation. So why we have to study them in a different subjects or separate subjects? Therefore he combined them, and that is it leads to the unification. Already in first PSC you have studied the unification is nothing but the combining the subjects which are related. So this leads to the unification of electricity as well as magnetism, and this new branch itself is called as electromagnetism. So electromagnetism is nothing but it is the magnetism which is due to the electric current in the conductor, that is called as an electromagnetism. And how this Ørsted has demonstrated, that we will discuss regarding this, that is the Ørsted experiment. So Hans Christian Ørsted, he demonstrated that magnetic effect of a electric current, means both are related, means how the magnetic effect will be produced in case of electric current. For that he has considered a magnetic needle. Whenever a magnetic needle, if you keep free, it will be standing in a north-south position. So consider a magnetic needle NS which is free to rotate about its axis, then a conducting wire which is held over the magnetic needle, then or which is held parallel to it. Just you observe these two diagrams, the first diagram and the second diagram. The first diagram, the magnetic needle, that is north-south position. Second also the same diagram we have taken, but the conducting wire, in the first case the current which is flows from A to B direction, and in the second diagram it moves from B to A direction. Then the deflection also goes on changes. How it will be changed? Just see the observations of Ørsted experiments. So the Ørsted observed when a current flows from A to B, the magnetic north pole that gets deflected towards the west side. Similarly, when the current which flows or which reverses from B to A, then the magnetic north pole that will be get deflected towards the east side. The deflection of needle that can be increased on increasing the current or bringing the wire as well as the needle very closer to each other. So with the help of this you can also thinking, that is whenever the magnet that will start to deflect, means yes, of course there must be another one magnet. So magnet that will attract the other magnet itself. So whenever the current is flowing in the conductor or in the wire, of course the magnet will be deflected towards itself, means of course there will be certain magnetic field. So that is the conclusion here. Since the magnetic needle or the compass, it only deflect by another magnetic field, thus it concludes that the current passing or the charges which are flowing through the wire, they can produce a magnetic field in space around the wire. So whenever the current or the charges which are moving, automatically they will produce a magnetic field around that conductor in the free space. So with the help of that magnetic field, automatically the magnetic needle will start to deflect. So this is what his conclusion, and the direction of the magnetic needle that will be given by Ampere's swimming rule, how it will be deflected. So that will be given by Ampere's swimming rule. So that definition is there, that is, imagine a man which is swimming along a wire in the direction of the current, with his face is always turned towards the needle, such that the current enters at his feet and leaves at his head, then the north pole of the magnetic needle will be deflected towards his left side. So, the same observation, east and west side we have taken the same thing, the direction will be given with the help of the Ampere swimming rule. Means whenever a person who is swimming along in the wire, the direction of current with his face is always turned towards the needle. So, such that when the current enters to his feet and leaves from his head, then the north pole of the magnetic needle that will be deflected towards his left hand side. So, this is what the direction of the magnetic needle that will be compared with a swimming person. So, that is given by Ampere's swimming rule. So, next we are going to discuss regarding what is magnetic field then. So, magnetic field already we know in the first chapter, the static charge is the main source for the electric field. But here whenever the charge flows, then only we are getting certain magnetic field. So, moving charge that produces a magnetic field. As soon as moving charge stops, automatically the magnetic field also stops. Thus, moving charges, they are the sources for the magnetic field, whereas the static charge are the source for the electric field. Then magnetic field, it is a vector quantity. Similarly, it obeys the principle of superposition and it is denoted by vector b bar, that is vector b, generally it is written as vector b. Then if the magnetic field, if it is emerging out of the plane of a paper, then it will be denoted by dot, or we can say whenever it is moving in a clockwise direction, means a magnetic field which is emerging out from the plane of a paper, that is clockwise. And if it is anti-clockwise, that is if a magnetic field is going into the plane of a paper, that will be denoted by cross, or it is an anti-clockwise direction. Similarly, we are going to discuss regarding the next concept, that is the magnetic force on a moving charge. So, just to observe both diagrams here. So, for that consider a charge plus q, means a positive charge, which is moving with a velocity v in a magnetic field B, such that V, which makes an angle theta with a B, that is a magnetic field, then the charge that will be experienced, the force that will be given by, generally the electric field force will be given by F is equal to Q into capital E. Yes, here the magnetic field will be come into picture whenever the charge is moving with certain velocity. Therefore, Fm, that is a magnetic force, that will be given by Q. Yes, of course the charge is required, but this charge is moving with a velocity, that is V cross B. So, this is what the magnetic force, however, we are giving. So, Fm is equal to Q into V cross B. Next, so this is what it is called as a magnetic force. Then this magnitude of magnetic force, that is Fm, that will be given by, sorry, the vector form is not written here, but is misprinted. So, only the Fm you have to take, that is Fm is equal to QVB sin theta. This is the magnitude of that. Fm is equal to QVB sin theta because it is a cross product. Then the direction of Fm is perpendicular to the plane containing V and B. So, always the direction of the magnetic force, it is perpendicular to the plane which is containing V, means the velocity, and the magnetic field. So, this can be also given by the right hand thumb rule, that is the right hand thumb rule. Already in 8th, 9th, 10th you have studied. The direction of this will be given by the right hand thumb rule also. So, just you go through with your right hand thumb rule on the, or a right hand screw rule in your 10th book. Next, the special cases for the magnetic force, that is Fm. What are the special cases? First one, if the charge q which moves parallel or anti-parallel, that is Parallel means theta is equal to 0 degree and anti-parallel means theta is equal to 180 degree. So once they are moving, then our Fm is equal to, it is QVB sin theta. So here QVB sin theta, theta is replaced by 0 or 180, then you are getting the answer as Fm is equal to 0 itself, because sin 0 is 0, sin 180 is also 0. Therefore, whenever the charge Q, once it moves parallel or anti-parallel, then of course we are getting the force is 0. Thus, there will be no force is experienced by the charged particle which is moving parallel or anti-parallel to the direction of magnetic field. Coming to the second case, that is charge Q which is moving right angles to the magnetic field, that is theta is equal to 90 degree. Then what is the case? Fm is equal to QVB sin theta. So theta is 90, of course we know sin 90 is 1. Therefore, our Fm is equal to, it is QVB. Then it is the maximum force that will be experienced by the particle here, or the charge. That is the charge that will experiences a maximum force whenever both are right angles to each other. Coming to the third case, that is if theta is equal to 270 degree, then our Fm is equal to QVB 270, that is sin 270. Sin 270 is minus 1. Therefore, our Fm is equal to minus QVB, that is the negative force that will be experienced by the charge, that is minus QVB. Next, the fourth case, if the charged particle which is at a rest condition means V itself is a 0. Already we know the magnetic field will be produced whenever the charged particle has to move with a certain velocity. So in this case, if velocity itself is a 0, so V is equal to 0, then can you produce a magnetic field? No. So then the no magnetic force will be experienced. Magnetic field itself is not given, means not produced. So magnetic force is also of course 0. So the charged particle is at rest in the magnetic field, that is V itself is a 0, hence there is no magnetic force that will be experienced by the charged particle. So these are the conditions for the special cases of the magnetic force. Next, we will discuss regarding the definition of magnetic field. To know the definition, already we know the relation, that is magnetic force Fm is equal to QVB sin theta. From this relation, what is B is equal to? So B is equal to Fm divided by QV sin theta, where Q is the charge on the particle, V is the velocity of the particle which is moving in a magnetic field P. Now, if Q is equal to 1, V is equal to 1 and theta is equal to 90 degree, then sin 90 is 1. Therefore, our B is equal to Fm we are getting. Then the magnetic field B at a point that will be defined as the magnetic force that will be experienced by a unit charge which is moving with a unit velocity at right angles to the magnetic field. Whenever we are going to define such a concepts, all have to equate to the 1 or unity. So magnetic field at this point that will be defined as the magnetic force that will be experienced by a unit charge which is moving with a unit velocity at right angles to the magnetic field. Then we will discuss how to write the dimension formula for the magnetic field. So magnetic field, that B is equal to Fm divided by QE sin theta. Already we know this. Fm means the magnetic force. Magnetic force means generally the force equation we can take, divided by Q. Q is nothing but the charge. V is the velocity. Sin theta, we don't have any dimension formula for sin theta. So for B is equal to, the dimension formula for force is already we know, that is m raised to 1, L raised to 1 and T raised to minus 2, divided by the charge. Charge is nothing but A raised to 1 and T raised to 1. Similarly, velocity is L raised to 1 and T raised to minus 1. Whenever we will get cancel the terms and divide the terms, we are getting that B is equal to m raised to 1, T raised to minus 2 and A raised to minus 1. So this is what the, similarly T raised to minus 2 is also there, that is m raised to 1, t raised to minus 2 and a raised to minus 1. So this is what the dimension formula for the magnetic field. Next we will discuss what is SI unit of magnetic field. So SI unit of magnetic field is a Tesla. So 1 Tesla, that will be defined as, that is, if a positive charge of 1 coulomb which is moving at right angles to the magnetic field with a velocity of 1 meter per second, then it experiences a force of 1 Newton. That is, B is equal to, if B is equal to 1 Tesla, when it will be possible means, if Q, that is charge, is equal to 1 coulomb and velocity must be equal to 1 meter per second and theta is equal to 90 degree, and it will experiences a force of 1 Newton. Means if a positive charge of 1 coulomb that will be moving right angles to the magnetic field with a velocity of 1 meter per second, then it will experiences a force of 1 Newton. So this is nothing but the definition of 1 Tesla. Don't get confused with the definition of magnetic field and the SI unit of magnetic field. Just magnetic field definition, just you equate with a 1 and write it, and SI unit of magnetic field means you have to define the Tesla. Another method is the Gauss, that is 1 Gauss is equal to 10 raised to 4 Tesla. Similarly, next we are going to discuss regarding the Lorentz force. This is also very important for 2 marks. Lorentz force means when a charged particle which is having a charge q which are moves in a region where both electric as well as magnetic force that will exist, then it will experiences a net force. That net force itself is called as the Lorentz force. Lorentz force means when a charged particle, if it is, of course, if it is moving means it will experiences a magnetic field. But at a certain region what happens, both electric as well as magnetic field both will exist. Then the net force that will be experienced by that charged particle itself is called as the Lorentz force. And that Lorentz force we can write it as, Lorentz force is equal to force on a charge due to electric field plus force on a charge due to magnetic field. Therefore, we can write it as it is F is equal to Fe, means force due to the electric field plus Fm, that is force due to magnetic field. So what is force due to electric field now? That is electric field force or electric force. That is a charged particle which is having a charge q and placed in an electric field E that will experiences a force. That force will be given by Fe is equal to Q into E. Already you know this in our first chapter. So Fe is equal to QE. Then the magnetic force Fm, the magnetic force will be given by, how the magnetic force will be written? So the magnetic force on the charge q moving with a velocity v at a certain angle theta with a magnetic field B, then that will be given by Fm is equal to q as it is. Yes, of course it is moving with a velocity in a presence of magnetic field, so V cross B. Lorentz force is nothing but what? It is the net force that will be experienced by electric as well as magnetic field. So the Lorentz force F is equal to, we can say it as Fe plus Fm. So F is equal to, what is our Fe? It is QE plus Fm is Q of V cross B. So Q is common, take it out. So F is equal to Q is common. Left out term is E plus V cross B. So this is called as the Lorentz force. Now the Lorentz force only in case of a magnetic field, that will be given by F is equal to Q of V cross B. So this is only in case of magnetic field, but the Lorentz force is nothing but it is net force when both electric as well as magnetic force fields are exist in that region. Coming to the next concept, that is the magnetic force on a current carrying conductor. This is also very important derivation for 5 marks. So in this case we have to consider one conducting rod of length L and an uniform cross sectional area capital A in an external magnetic field capital B. Let the number of density of mobile charge carriers, or we can say the electrons, be n number. So n number of electrons which are present over here. So just to understand here, the magnetic force on a current carrying conductor. So one conductor we have taken, that is a straight conductor or a rod of length L and uniform cross sectional area A, and similarly which is present in a uniform magnetic field B. Then the number of electrons which are present over that is nothing but n number of electrons, they are generally there we are telling. Then the total number of electrons which are present in that entire rod, that will be given by NaL, that is n number of electrons which are present in an entire area and which are present in the entire length. Therefore entire rod we are getting the total number of electrons are NaL, and if Q is the charge on each charge carrier, so electrons are having a charge, so that is nothing but Q is the charge on each charge carrier, then our equation becomes NaLQ. So it is NaLQ. Then when a current I which is flowing through the conducting rod, then each mobile charge carrier which is moving with an velocity. So whenever the current flows through the conductor, current flows is nothing but the charge starts to flow and they are moving with certain velocity. That velocity here we can take it as it is an average velocity. That average velocity we called it as it is drift velocity. So drift velocity we can represent in the form of Vd. So that will be in the presence of external magnetic field capital B. Then the force on these charge carriers, how to write the force on these charge carriers now? So F is equal to, general our equation is Q into V cross B. So our Q is replaced by, there are n number of electrons which are present in entire area, which are present in entire length, and they are having a charge Q. Therefore instead of Q we have written it as NaLQ. V cross B is common. So here the velocity of individual electron we can't take, the average velocity of all the electrons we have taken, that is nothing but the average drift velocity. Therefore it is Vd cross B. So our F is equal to Q of V cross B. The same equation whatever we are writing, the same equation will be replaced here. F is equal to NaLQ Vd cross B. So but now we know that is NQVD. N means the total number of electrons, that is n number of electrons. Q is the charge on electron and how they are moving, velocity Vd, that is drift velocity. This is nothing but the J. This equal to J, that J is nothing but the current density. Now our equation becomes now F is equal to, N is left out, Q is gone, Vd. So left out term is AL. Instead of this NQVD we have substituted it as J cross B. Now the magnitude of J, that is current density, that will be given by, current density is nothing but J is equal to current per unit area, that is I divided by A. So substitute the value. One thing you remember here, the current is not a vector quantity. So our equation becomes F is equal to AL. Substitute the J value is I divided by A cross P. So in the next step, A get cancels. We are getting F is equal to L of I cross B. But the current is not a vector quantity. We can replace our equation as F is equal to I of L cross B. Length is a vector quantity. Therefore, our equation becomes F is equal to ILB sin theta, because it is a cross product. So theta is the angle between L and B. So next we are going to discuss regarding the cases. So if theta is equal to 0 or 180 degree, what happens? Means the force is 0 when the conductor is parallel or anti-parallel to the magnetic field. Therefore F is equal to ILB sin 0, that will become 0. Means both, that is whenever it is parallel or anti-parallel to the magnetic field, the force experienced will be 0. Similarly, second case, the force is maximum when the conductor is perpendicular to the magnetic field, that is theta is equal to 90 degree. Therefore F is equal to ILB sin 90, then you are getting it as ILB itself. So equation 1 which is, or equation 2 you can say, both, they are holds good for only the straight conductor. Suppose if the conductor which is made up of any arbitrary shape, so it is only holds good for the straight conductor or the straight rod or straight wire. But if that wire is made up of certain any arbitrary shape, then it can be assumed or it can be considered that it is made up of large number of linear strips of length dl. So instead of L, now you have to consider they are made up of small strips, that is called as dl. Then the vector sum of this I, that is dl cross b, we have to take, then we have to take it as the summation or the integration. That is if the case it is not in the straight wire. So this is regarding the magnetic force on a current carrying conductor. Thank you.